Hi, in today's video, I'll be continuing our journey into abstract mathematics at a beginner level. And so, previously, we had done how to do certain proving techniques. And now, I'll show one more very important proving technique in mathematics. This is known as mathematical induction. Mathematical induction is a way for us to help answer questions where there is an infinite list of statements. So you can think of it as a for all question, as a for all proposition. For example, you want to know whether the sum of the first n odd integers equals n squared. Well, you can write it out and see that the pattern holds true, but that does not prove the statement because you want to know that it holds for a general n. And so, while you can say that you are able to prove it directly, by assuming nothing about n, you will not be able to start, and you do not have any other assumptions that you can make using n to help solve it. And so, this is where mathematical induction comes in, where now you prove a base case that is known as your S1 or P1, depending on what you want to know it, like statement 1 or proposition 1. It doesn't matter what you name it, but you must start with a base case. And so that is your first statement that you want to prove. After you prove your base case, you can imagine it as a domino being knocked down. And so your first case knocks down, as the photo shows below. Now you assume that SK holds true. So statement K holds true, and you want to prove that SK plus 1 holds true. So because now you have an assumption of SK being true, if this SK is true, it will knock down, and if you're able to prove that SK plus 1 is true, it will knock down as well. You'll be knocked down as well, and it will then knock down SK plus 2 and so on. And so you can see from this picture how all the SNs for any n holds true. Because your first one is true, it will cause the second one to be true, third one to be true, fourth, fifth, and so on. And so you just need to prove that the base case is true, and you need to prove this step. This is called the inductive step. You need to prove that the inductive step, where you assume the inductive hypothesis SK is true, leads to SK plus 1 is true. And so essentially it's proving S1, and you're proving this statement, SK implies SK plus 1 is true. Hence, this is the simple idea behind mathematical induction. Let's see how we can use it in solving problems. So, we want to prove that the sum of the first n odd integers is n squared. Like I said, we first prove our base case. So our base case is n equals to 1, which is usually very trivial, but not all the time. And then we now want to prove this statement, SK implies SK plus 1. So we can assume we have some assumption now, so we know what SK looks like. Now we want to prove this statement. And then it follows that this is just an implication, conditional statement, and we can prove it directly. So, because SK will be inside this SK plus 1, we know this part is SK, and so this reduces to K squared. You can just simplify this and you get K plus 1. And so, by proving this statement and the base case, you prove all the cases for any natural number. And this is the essentially how anything to do with the natural numbers are proven. You can read up more on induction and how induction was formulated because of how the natural numbers was formulated. But that's left to axiomatic set theory, which is too advanced for this basic tutorial. In this tutorial, we will instead just show you how to be familiarized with proving using mathematical induction. And so, there are other forms of mathematical induction, because if you understand the domino picture, you can see that your base case doesn't need to be always start from s equals to 1. N equals to 1, I mean. It could start from n equals to minus 4, and if you are able to show sk implies sk plus 1, it means from minus 4 all the way to minus 3, minus 2, all the way to infinity, all those numbers cases will work as well. And so, let's just say n is a non-negative integer. In this case, it means n can start from 0. So our base case is 0, we prove it holds true for base case 0, and we prove that it holds true for all. You can read this simple example, and I'll go on to a more fairly important theorem actually. This is known as Belloni's inequality, where 1 plus x to the power n, where n is a natural number, is always larger than 1 plus nx. This inequality is very famous and has been used in countless other fields. And so let's try to prove this important theorem. So, as we have said, in this case, x here is just a dummy variable. It doesn't need to be anything. And so we want to do induction on n instead. So for our base case, n is 1. Is 1 plus x larger or equals to 1 plus x? Well, that holds true. And so we want to prove the inductive step. Hence, we assume the case that n equals to k is true. Means we have this statement is true. Now we want to prove that 1 plus k, x to the power of k plus 1 is larger than 1 plus k plus 1 times x. Well, since 1 plus x is positive, since x is larger than minus 1, we can multiply both sides without changing the inequality sign. And so we have this. This side is now what we want, and if we reduce this further, it becomes 1 plus k plus 1x plus k x squared. However, we know that x squared is positive and k is positive. And so, this portion on the left hand side will still be larger or equals to 1 plus k plus 1, 1 plus k plus 1 times x. And hence, we get our inequality. And so, this proves that for a general n, this inequality holds true. More about induction is the formulation of strong induction. If you see that we want to prove the statement that sk implies sk plus 1, sometimes it might not always be good enough to help us prove the next step, because sk is our only assumption. And so we introduce more assumptions, and this is the idea of strong induction. Instead of just assuming sk, we assume that all the previous term holds true, and this implies that sk plus 1 holds true. With more assumptions, it can lead to the proof being easier, even though you might not use all the statements here. The idea is still the same as the domino, where because you have one base case, it leads to another falling, but now these two falls allows the third one to fall. And it's actually just the same idea as the domino effect. So there are many actually variants of induction that you can use, and you can read more about it on Wikipedia, but the two most common people uses are the ordinary induction that I went through in the beginning, and this strong induction. This shows you why sometimes the SK case might not be enough. Because if you want to use the ordinary induction, you are unable to get how k cents can help you get k plus 1 cent, since there's a 1 cent difference and you only have a 3 cent or 5 cent stem. And so you can go back 3 cases earlier. So k minus 2 can imply k plus 1 is true, because now you can just add a 3 cent stem. And so with that, you need 3 base cases to hold true, which is 8, 9, and 10 first, which then will cause 11 to be true, 12, and so on. A very, very important use of strong induction would be proving the fundamental theorem of arithmetic, which will just prove existence and uniqueness follows from the division algorithm. So the existence portion, we just need to do the base case first, n equals to 2, which is already prime, so it's its own prime factorization. Now, consider n plus 1, and we are using strong induction, so all the integers from primes from 2 to n, all the integers from 2 to n have a prime factorization. Now, considering n plus 1, if it's prime, it is its own factorization, so we're done. If it's not prime, then it can be broken down into 2 factors, because that's the definition of coprime. Because a and b are less than n plus 1, they lie in what we have assumed to be true. And so they have prime factorizations, and when you multiply them, that is itself a prime factorization. And that completes the proof. And this is how you can see how strong induction is really useful when the previous case is just not enough and you need to go back a few cases. You can see question 15 in the book for more examples on how to do it, and this is the outline of the proof. Now, there are some fallacies that you need to take note. If the base case doesn't hold true, then you can see that the domino effect will not happen, because the first case doesn't fall, leading to the second case unable to fall. And so, it's very important that you prove the base case first. Even though sometimes the base case might be trivial, as you can see, n equals to 2 is already its own prime factorization. But in other cases, it is very important to not fall into this fallacy. Another fallacy is when sk does not imply sk plus 1. Then obviously the domino effect doesn't even hold true, and so you cannot use it. And so these are some certain fallacies that you need to take note of. But if you stick with the logic of proving your base case first, and then moving on to proving your inductive step of something implying sk plus 1 is true, there shouldn't be an issue, but you do need to remember. That's all for today's video. I hope you have learned something about induction. Do practice more in the textbook provided, and see you again next time. Thank you.